My name's Dan Warner. I'm joined today by Seb Lesware, who's One Spatial CTO. It dawned on us today, actually, it's a bit frightening that between the two of us, we've got 50 years of experience within the industry, which is a little bit shocking because that means we're getting very old. But anyway, the agenda is that we want to set the scene for managing 3D data in the context of 2D data to start with, and then we're going to build on the demo that we showed last month at the 3D GeoInfo conference. So we're going to look at how you validate 3D solids, how you can automatically inspect your 3D data in the context of your 2D data, and by that it's sort of looking at is the feature that's represented by your 3D geometry the same real-world feature as that feature that's represented by the 2D geometry, or is it actually in fact a form of change intelligence? We're also going to look at how you can undertake PAI, so positional action improvements, to shift maybe shift your 2D data to align with your newly captured 3D data. And then finally, we're going to look at how you can build new insights into 3D data by combining it with a completely new data source. An example that we've picked is we're going to introduce a floor plan, and we're going to use that floor plan to infer the buildings within the building geometry, within the building solid. We're also going to be running a poll today. It's just to enable us to get a bit of an insight into the 3D industry and the maturity of the 3D industry. We've got 4 questions and they'll be scattered through the presentation. So we're going to run the first one now. And the first question that we're going to ask is, are you planning to manage 3D data alongside your 2D data? So I think we've got our feedback on that, which is great. Okay, so let's start with the webinar. So globally, we're seeing governments rethink how public services are delivered to solve the new challenges that we face. So this can include in investing in automation to deliver existing services cheaper, faster, more reliably, but more importantly, it's delivering new services at a community level or regional level or national level to meet the effects of global challenges. So for example, climate change, sorry, I'm just going to move my slide back on. Climate change, such as flooding, wildfires, sea level, increases in sea level, migrant crisis, COVID, global recession. So there's all these sort of big global changes that are happening, and governments around the world are needed to react to those. And to rebuild the approach to deliver these public services, it's now recognised that to understand the context of the decisions that these services make, we need to understand the place, the region, and the communities where these decisions have an effect. And so obviously a key tool in understanding place or our communities is spatial data, so a map. But these spatial data sets need to be trusted. They need to be authoritative. And they need to be authoritative because they underpin public expenditure, and more importantly, they inform the decisions that affect the individual citizen, so the decisions that affect you and me. And this is a real challenge for the data stewards of the world's authoritative data, as there's not one data set that has all the answers. So therefore, that's a real opportunity where 3D data can help, because 3D data is fairly fast to collect. It's relatively cost efficient to capture. And when combined with other authoritative data, it delivers new insights and new perspectives that we didn't previously had. And the result of combining those data together is that it enables the public services to have a greater impact on the communities where they're delivered. So, by using 3D data with authoritative data, we can visualize new things. So an example could be using 3D visualization to improve the way that we undertake planning. So how we deliver better services to the communities, so schooling and housing, or how we can improve flood modelling. For example, does the flood model take into account underground car parks and underground dwellings, which can be captured in 3D data? And this in turn informs and aids the emergency response. And it affects, it also, by combining your 2D and your 3D data together, it provides a base layer for things like smart cities and digital twins. So what we're going to be looking at through this webinar is how we can combine our 2D data with our 3D data in a coherent way, that it sort of forms these platforms that enables you to bring in different data sources to make new and different decisions. And that's the webinar that's the demonstration that Seb's going to walk through by using One Integrate. But just before we step into showing that demo, what I would like to do is just ask our second question of the day, which is, what is driving your investment into 3D data? So I think we've got the answers back to that. So we've got answers to the poll. Thank you very much for contributing to those. So we've had, given an overview to where 3D data can help sort of this changing to the public services that are being delivered across or globally. And now what Seb's going to show is how you can bring in your newly captured 3D data and coherently manage that with your existing 2D authoritative data.
Thank you, Dan. I'm just going to share my screen. So what I'm going to show you now is I'm going to be using our One Integrate, our rules-based product, to show how we're going to manage and balance these two sets of data. Right. So let me just share the right screen. Might not be the right one yet. Can you see my screen, Dan?
Yes, Seb, we can see your screen.
Yeah, there, perfect. Okay. So I'm going to show One Integrate working on data. So this is a demonstration we've got using data from Ordnance Survey of Northern Ireland, and we've got some 3D sample data from them, and also some 2D data. And we've made a few changes to it to show some of these concepts. So this is a fairly common scenario where people are managing 2D data, and they have been for a long time, and we don't expect that to go away. People will be generating, requesting, and using 2D data for plotting on maps, for doing lots of business processes. But at the same time, organizations want to enhance that by storing a 3D version of the data as well. And typically that starts with buildings. That's the most common thing. Lots of the use cases for 3D data are centered around buildings, and they tend to be the most sort of structured things in our data and typical things we manage. So here we can see we've got data that is the 2D footprints underneath, and on top of that we've got the 3D buildings, and they're captured in a whole bunch of different ways, typically a mixture of ways in an organization. So sometimes they're extruded. You take the 2D data, you extrude it, generate a 3D plan, which gets you some of the way. Here for example, you can see we've got more than that. We've got actual shapes of the buildings, including roofs, roof surfaces, floor surfaces, traditional sorts of city GML data structure. And so we've got more information than just you'd have for extruding the 2D data. So these could be captured by LiDAR, they could be coming in from BIM models, they could be coming in from a sort of a point cloud scan that gives some heights. It could be modeled manually. There's all sorts of sources and reasons why the data's captured and managed. So we've got what I've got is a one integrate session that's running on some data, 2D data, 3D data, and we're going to be doing some things. We're going to be doing some data quality enhancements, some positional improvements, some data improvements, and then also some enhancements of the data to generate new things that we didn't have before. So what we're looking at is the one integrate. It's just a simple viewer to allow us to have a look at our rules and see how we're doing, almost like a debugging business process tool for making sure we're doing the right rules. What we're actually doing though is running. This is a one integrate session, which is doing a series of tasks. It's loading some data and it's processing, running some rules to check the quality, and then doing some enhancements. So the first thing I'll do is our third of 4 polls. We're going to ask a question now about data storage and formats that are handled. While that's happening, I'll keep talking. I'll give a few backgrounds, some more background information. So we see that there is a desire, and there are lots of different drivers for why people need 3D data. In the past, people have struggled to find a good business case for it. Everyone felt like it was going to be useful, and we're not quite sure the best ways it's going to be used. And some people use them for fly-throughs and tourism, but more and more it's about things like taxation or energy efficiency, or sound pollution, all sorts of modeling that we see being used in a sort of smart cities context for this 3D data. So there we go. We've got some information back. Thank you about the formats people use for 3D data for data exchange. So here we've got, if I share my screen again, let me just check. Okay, yeah, there we go. So in this scenario, we've loaded 2D data, we've loaded 3D data, and then we have a session that's going to do a bunch of checks. So for example, we're validating that other 3D solids themselves valid, and the data we've loaded is that fundamentally valid. And some of the other checks that we're doing are things like consistency checks. So we are saying that in this data, there is the 2D buildings have a number of floors attribute, and we're saying, does that correspond to the height of the 3D building that it seems to be coincident with? So if it's a 10-story building, then we'd expect it to be more than 4 meters in height, for example. And if it's not, then there's something inconsistent. Either the 3D data is wrong or the 2D data is wrong. And then we can use information that we know as data custodians about that data source to know actually which one is more likely to be correct, and therefore which of the 2 sources are inconsistent. And then we're doing some other checks. Now, one of the checks we did here is, does my 3D building exactly match, does its footprint exactly match the 2D building underneath it? Because there should be a roughly one-to-one correspondence between the two. And if you do an exact match, you get none of them match exactly. And you'd expect that, because unless you have just done a very simple extrusion of your data, just the fact that you're using different tools, you've got 3D data, it's got more complexity. It might also be more positionally accurate. It might also be have more detail in it. It's very unlikely that you'd get an exact match, but that's okay. We need to deal with that ambiguity. So then we do a second check, and we say, well, okay, within a tolerance of 30 centimeters, can you show me which buildings match? And if we do a 30 centimeter tolerance, and if we go back to our session, we can see these percentages. So 0% at exact match, 59% match when we do a 30 centimeter tolerance, and 81% match when we do a 1 meter tolerance. So, okay, that's interesting. That sounds like some interesting results that we want to see. So if we go and have a look at the results of the 1 meter tolerance match, we can step through and we can have a look at some of these. So this is one example. And if I turn off this perspective, so we get a 2D view, you can see these are just differences in the footprint of the building. The 2D building is just sticking out there beyond the shape of the 3D building. Other examples, I'll turn the perspective back on. Other examples are, well, here's a good example of there is no 2D building. If I turn off the 3D, you can see there is no 2D building underneath. So that's just a real world change. Something's been built, it's not been captured in 2D. And depending on our knowledge of either the whole data sets or maybe individual cases, so we might look at a date captured field as metadata on the whole data set or just on that object, tell us, well, actually there is something missing in 2D, and therefore we can update the 2D based on the more recent information in 3D. And we see that quite commonly because the techniques used to capture 3D often involve scanning, which tends to be a bit more automated and tends to be a bit more up to date and more positionally accurate because of the modern tools. Then often it's the 3D data that can inform the 2D data. So here's a good example. This is an artificially created one, but here we're showing an offset. The 2D data doesn't match the 3D data. Now there's another ambiguity here, or another difference. So these 3D objects are represented as different parcels, one for each building, potentially each address. The 3D object is one contiguous building. So there is a modeling difference, a structural difference between these, but that's okay. You know, if that's our 3D data model, maybe we accept that, or maybe we want to split it up. But we can see visually, we can see that there is a correspondence between the two. So that's a positional accuracy difference. We'll go back to that in a moment and show how we can correct that. Another examples are just real world change. So here are a number of presumably residential buildings that have been knocked down and something has been built in its place. A clinic maybe has been built in its place. So that's a genuine real world change. And again, we might decide to say, well, we know the 3D data is more up to date, and therefore we can produce rules that will automatically deal with that. I could just report it to my operators. That's some change intelligence that we're generating on the 2D data. But we could also write rules that automate that to say, well, I'm going to remove these 2D objects and I'm going to generate automatically the footprint of the 3D building, and then I can stitch that footprint into my existing skin of the earth data. So I will then fill the gaps and merge in and stitch that in new information into the underlying data, and then I'll therefore have an updated version of my 2D data automatically from the 3D. And some of these, yes, are just positional differences or absolute differences. Okay. And some of them are fairly subtle, and so this is where we're doing a check of what 1 meter difference. So it's subtle, but it's still a big difference, and that gives us some interesting insights into the quality of our 2D data and our 3D data. So let's go back to the example that we had before, which showed a positional offset. Okay. Now, what we're interested in is, well, can we use that information to automatically update the position of the 2D data? So what we have in this session is we've got a process which can look at where data is equivalent and determine that the only difference is an offset between them. And we can generate shift vectors that represent those differences in data. So here, for example, we've taken the 2D data and we've merged all the contiguous adjacent 2D objects into one essentially block, 2D block, and then we can compare that with the footprint of this 3D block, and we can say, is there a good correspondence? Are they the same sort of shape, the same sort of area? Okay, well, I have an equivalent thing here that's just positionally different. So if they're positionally offset but the same shape and area, once you ignore the encoding, then the rule has automatically associated the two, and it's calculated the shift vectors we'll get from A to B. Importantly as well, we've got these points generated, and these are the points that represent a no shift. So we don't want to accidentally shift all the data around it if it doesn't require an update. We're only updating the specific parts of the data that require it, and we're anchoring all the bits of the data that don't. And then what we can show is after we've calculated these shifts, then we're shifting the data, and we can see it sort of sliding. So I can step back and forward, sliding back underneath the buildings. And now there is a good correspondence between those buildings. And that shows up in the statistics for my session. So before I did the shift, I had an 81.63 alignment between my 2D and 3D data if I take a 1 meter tolerance. But after shifting the data, I've now gone up to 89.79%. So what that tells me is I've eliminated those sorts of problems, and therefore what I have left in my report are the differences that can't be attributed to a simple positional shift. So I've automatically resolved some issues, and what's left are different issues. And I'm now might want to run some rules that deal with those. I want to flag it up to a team that can deal with them. It's up to me as an organization how I deal with that. Okay, so that's one use case. That's improving 2D data based on 3D data, and typically it goes both ways. We would help to generate missing 3D data by extruding. We would be taking the data or improving the 2D data by the positional accuracy of 3D. Now, if we look at a second use case, so this second use case is about generating data, 3D data that's more the split up according to the information in 2D. So for example, if we have a look at this terrace of houses, that is one object in 3D, but underneath there are lots of separate 2D objects that represent them. So we'd be interested in splitting that up to represent properties, but actually we can do more than that. We can say, well, I want the individual floors of the individual apartments in that building. So what we can do is we can have a look at, say, if we can take the roof surfaces, because that's going to help us to do some approximation. Then we can say, well, I want to generate different floors in a building. Some of the buildings, some of the 2D buildings have information coded on them about how many floors exist. So some of them have a number of stories attributes. Some of them do not, and therefore we can infer stuff. So we can infer information if it's not there. So I'm going to infer that I'm going to measure the height from the bottom of the 3D building to the bottom of the roof. That is the living space for this property. And because the 2D version is encoded as domestic, I can say I'm going to assume there's approximately 3D height for a floor on a domestic building. So how many floors could I fit on the height of that building? Other buildings, for example, this one is much taller, and it's classified as commercial, and therefore probably it's an average of 4 meter height. If the 2D version has encoded in it the number of floors, great, I can work that out explicitly. But if not, I can make a good approximation. And we can split the data up based on the footprint of the data. And here, for example, we've got the internal floors that will show us if I turn off the roof surfaces and jump to the bottom of the end of my session. Then we've generated the 2D floors, 2 floors for each property in this 2D building, and that's using the 2D topographic data. But actually we've got some additional information, or at least we've simulated some additional information here. So if we have a look at, we've got another set of data, which is the footprint. So let me turn off there. So we've got simulated in here some footprints which would have come from some CAD data, so some floor plans. So these might have come in as polygons, might have come in as lines that we formed as polygons, and this represents, and these are essentially just 2D information that exists at sort of 0 on the ground. But each floor plan will know I belong to floor number 7 for this building. So we might need to positionally shift them, but then we can use that floor plan information to create internal spaces based on rooms, for example, and that becomes useful for things like emergency evacuation plans or building heat efficiency. So if we have a look at the internal floors that are generated for this building, so the others were based on the 2D topographic information. This building's been split up according to the information in 2D, and there are lots more details. So for example, this floor plan had some small rooms there at the bottom. The floor above it had larger rooms. The ground floor has different rooms to the floor above it, and that's just created by taking the floor plans, moving them to the right height, and extruding them, and filling the space that is bounded by the 3D volume, but defined by the floor plans that lie underneath it. So we're going to go to our final poll now, which is again talking about data storage formats. So this data happens to have been loaded from an Oracle database. So they are 2D, 2.5D, and 3D solids coming from an Oracle database. But typically there are numerous sources that people get data from and exchange data. So and typically there are two things that we're interested in. One is, how do you exchange data? So give it to customers, or provide it, or exchange it, or ingest it. And then how do you store data and manage it? And often that's stored in a database. You'll notice we don't have SQL Server in that list because that doesn't store 3D volumes. You can store 2.5D data. It might be coming from CAD formats. It might be stored as files in a CAD system, or stored in a GIS geodatabase. That list could be much longer, but we've put some of the most commonly encountered ones there anyway. So what we've done is we've looked at the quality of the data, and we've measured it, and we've improved it, and we've reported on it. And then we've also generated some new information based on taking the 2D and the 3D data and enhancing it, and that can now be published and used for all sorts of tasks, such as, and we've seen examples of people doing things like taxation. So do I have a C view? I pay more tax in that case. How much tax is this person paying? Okay, well that looks like they're paying more tax than their neighbour that's living in the same apartment block. Or what about solar panels? How many solar panels do we think we can fit on southerly facing roofs? Or what's the efficiency of this building approximately based on its age, its surface area, which way it faces, how much shadow it falls in? Okay. So that's what we wanted to show to you today. If you have any questions, then please say so in the chat. If we have, please get in touch directly as well if you want any follow-ups or you want to find out more information.
So, Fee, do we have any questions coming through?
Right, so there is one question. It says, you mentioned in the presentation underground car parks and dwellings, but it wasn't in the demo. Can you support modelling underground features?
Yes. So this is all about the information that's stored. So here, for example, the stuff we were seeing was 2D footprints that represent something that's on the ground. And the information was how high up they go. If you have a 2D building that represents information that's underground, and therefore you've encoded it as this is, the lowest point of this is -20 and the highest point of this is -10, then the maths all just works out, and these go down rather than up. What we see usually in these scenarios, people tend to be talking and sharing data about above ground information, but actually if you look at, say, the utilities world, they're mostly interested in what's below the ground. Or if you're building a new, I don't know, a tube line, you care about what's below the ground. But essentially it's the same approach, the same process. You're just going down rather than up.
Great, thank you. I don't think there's any other questions unless anyone would like to raise their hand.
Okay,
that's everything.
That's the end of our presentation. I'd just like to take this time just to raise awareness that we're running our conference, Smarter Data, Smarter World, from the 9th to the 12th of November, where we will be talking more about the management of 3D data with authoritative data, and we'll be showing more of some of the innovations that we're doing across the piece. So if you're interested in joining our conference, and it'd be great to see you there, then you can register now, and hopefully you can see the slide up. But other than that, thank you for your time today. And if you do have any questions about what you've seen, then please contact either myself or Seb, and we'll respond as soon as we can. So have a great day, everyone, and thank you for your time.
Thanks, bye.